Okay, we're back and we're going to talk about hemicontinuous correspondences. Now, hemicontinuous correspondences are foundational for the Kakutani fixed point theorem, for equilibrium in economics and game theory, and for the maximum theorem, among other things. So these are all important ideas that you're going to come across in probably your first course or second course in microeconomics. Now, what we're going to do here is we're going to take this definition of continuity for a function, a single-valued function that we're familiar with, and we're going to generalize that definition or convert it into a definition of continuity for correspondences. Now, I'm sure you've noticed already that two of the element symbols in this definition are I've highlighted in green, and the other two appearances of the element symbol I have not highlighted. And the reason for that is that the two highlighted green appearances of the element symbol, they're telling us about something that's happening in the target space with the image under the function f of the point x bar in the domain. The two unhighlighted appearances of the element symbol are telling us about something that's happening in the domain. And that is the key to being able to figure out how to generalize this notion of continuity to correspondences. And now, I want you to notice something about those two places where we've got a green element symbol. So we're talking about the target space, and so suppose that we have any element of a set V in the target space. It's completely equivalent to say the singleton set consisting of the element Y is a subset of V. They are the same statements. They're written differently, but they mean exactly the same thing. If Y is an element of V, then the singleton set consisting of Y is a subset of V, and vice versa. If the singleton set's a subset of V, then Y must be an element of V. And of course, here we've got this in terms of the images, so I'm going to rewrite the Y in terms of an image. And so f of x is an element of V if and only if the set consisting of f of x is a subset of V. And so with that, we can see that the star statement, the definition that we've given for continuity, is exactly equivalent to, it's the same statement as the A statement here. They're the same statement, just written a little differently, because f of x bar in V is exactly the same as the set, the singleton set consisting of f of x bar is a subset of V, and the same thing for the image f of x. Element of V, the singleton set's a subset of V. So we have two completely equivalent ways of saying the definition of a continuous function. Now, there is a second way that we could rewrite this in an equivalent way, and that is to notice that if Y is an element of V, then the singleton set consisting of Y intersected with V is non-empty. It's not the empty, it's supposed to be non-empty there, okay? Again, same statement. If Y is in V, then the singleton set consisting of Y intersected with V is non-empty, or the singleton set consisting of Y intersects V. And in fact, I'm going to write a kind of an ad hoc notation here. I'm going to make up a notation, intersecting symbol with a bar over it, like this. And we're going to say that means, so we're defining a binary relation between subsets of the target space, for example. This means A intersect B is not empty. I just want to have another way of saying this that is in terms of a binary relation. And so this means that I could say here, this intersects with V, and I could take this off. Okay, and that's the way I would read this. A intersects B. Singleton set Y intersects V. And so if that's the case for any element Y, it's of course the case for the element, which is the image of X. So this says f of X, f of X intersects V. Again, f of X intersects V, equivalent to f of X, the singleton set f of X intersects V, equivalent to saying f of X is an element of V. And so, therefore, we've got yet a third completely equivalent way to state the definition of a continuous function at a point in the domain. The B statement here says, just what we'd expect given what we said here, that the singleton set consisting of f of X bar intersects V implies the stuff down below, in particular, something about the singleton set consisting of f of X being a subset, intersecting with V. So these three statements are completely equivalent to one another so long as f is a function, single valued. But suppose that f is instead a correspondence now. So we want to generalize this from functions to correspondences. So if f's a correspondence, then f of X bar and f of X are both sets in the target space. They're no longer points or elements of the target space. So the first statement, the star statement, is completely meaningless now if f's a correspondence, because we can't say the set f of X bar is an element of the set V in the target space. So the star statement's out of the picture. So what about A and B? They are completely different as well. And in order to see that, let's notice that let's suppose that this is the set f of X, the image of X, or of X bar, doesn't make any difference here. And let's suppose that this is the set V. So we're in the target space here. And now, of course, f of X does intersect V. The sets intersect one another. The intersection is non-empty. But f of X is not a subset of V. So clearly, the statements A and B differ from one another because f of X bar is a subset of V and f of X bar an element of, intersecting with V, and the same for f of X. Those are different between A and B. So the A and B statements are different. And in fact, these two properties of a correspondence are exactly the properties that we use to define upper hemicontinuity and lower hemicontinuity. We say a correspondence is upper hemicontinuous at a point X bar in the domain if it satisfies the A statement, and we say it's lower hemicontinuous at a point X bar in the domain if it satisfies the B statement. Now, you should have noticed that, in fact, A and B are both meaningless statements as well. So I've kind of gone ahead as if they are what we said they were, but they're meaningless. And here's why. Because f of X bar and f of X, they are sets in the target space, subsets of the target space. But to write, as we do in A, that the set, the curly braces here, say the set consisting of the set f of X bar is a subset of V. Well, that is actually meaningless, and of course the same problem in B. And so what we need to do is we simply need to take off these curly braces so that the statement A begins f of x bar is a subset of V, because that's meaningful. So that's what I've done here. I have taken off those curly braces, and so now A and B really are the definitions of a correspondence being upper hemicontinuous at x bar or lower hemicontinuous at x bar. And in fact, we also say that the correspondence is continuous at x bar if it's both upper and lower hemicontinuous. Let's just say one or two more things before we look at a couple of examples. So we say that the correspondence F is upper hemicontinuous on the set X, or we sometimes just say it's upper hemicontinuous, implicitly meaning that it's upper hemicontinuous on the set X, if it's upper hemicontinuous at every x bar in X in the domain. And of course, that's just the same as what we do for functions. When we say a function's continuous on its domain, we mean that it's continuous at every point in the domain. And of course, we do the same thing for lower hemicontinuity and for continuity for correspondences. So now let's look at a couple of examples that I think will bring out the meanings of upper and lower hemicontinuity. Now I'm going to do the examples over here on the left side of the screen, but I have put the definitions of upper and lower hemicontinuity back over here so that we'll have those to refer to when we need them. Now, this first example is a correspondence from the unit interval into the unit interval. So its graph is a subset of the unit square, and you can see just by looking at the graph that it's a closed subset of the unit square. So that means that the correspondence is a closed correspondence. Also, notice that for every x in the domain, the image of x under F is either the singleton set consisting of just 0.5, or it's the closed interval from 0.3 to 0.7. Both are closed sets, so this is a closed valued correspondence. And so what about upper and lower hemicontinuity? Let's first focus on upper hemicontinuity. To say that the correspondence is upper hemicontinuous, or lower hemicontinuous for that matter, without saying where, means implicitly that it's upper hemicontinuous or lower hemicontinuous on its entire domain. So we need to show that this correspondence is upper hemicontinuous at every point in the domain, in the unit square. So the one place where it seems most likely that there might be a discontinuity is clearly at 0.5. So let's let x bar be 0.5 and try to show that the correspondence is at least upper hemicontinuous there. So we have, let's say, x bar equals 0.5. So f of x bar equals the closed interval from 0.3 to 0.7 at x bar equals 0.5. And so what we need to do is we need to show that for any open set V that contains this unit interval, this closed interval, that's f of x bar, that for any such open set, we can find an appropriate neighborhood of x bar down here in the domain. And by appropriate, I mean one such that every x in the neighborhood gets mapped into that set V. So it seems clear that any open set in the target space that contains the closed interval from 0.3 to 0.7 has got to at least include an open interval that is bigger, if you like, than this closed interval. So it has to be the open set V, if it contains this closed interval, has to include an open interval with the left-hand endpoint, the smaller part, smaller than 0.3, and the larger endpoint bigger than 0.7. So we have, and let's take as an example, let's suppose what we have is, just for example, the open interval from 0.2 to 0.8. So from about here up to about here, that open interval contains this f of x bar, the closed interval here, and it's clear that now for any x down here in the domain near 0.5, or for that matter, in this case, any x really, the image is still going to be either 0.3, 0.7 closed set, or the image is going to be just the singleton set 0.5. So it's always, in fact, going to be a subset of this open interval, 0.2 to 0.8, or more generally, from A to B, if A is smaller than 0.3, and if B is bigger than 0.7. So indeed, for any x down here, the image is still going to be a subset of V, so that establishes that the correspondence is indeed upper hemicontinuous at x bar equals 0.5. And of course, for any other point in the unit interval, if x bar is over here or x bar is over here, certainly if x bar is over here, the exact same argument continues to work. And if x bar is over here, well now we have to use not only these open sets, but we have to consider any open set that contains the image. And now the image is just the singleton set consisting of just 0.5. The image is just this singleton set here. And so every V that contains that has got to be considered, but for every V that contains the 0.5 in it, it's clear that we can move a little bit to the left or a little bit to the right, and the image, of course, is still going to contain the singleton set 0.5. So that establishes that for every point in the domain, in the unit interval, this correspondence is upper hemicontinuous. Now, what about lower hemicontinuity? If we wanted to verify that the correspondence is lower hemicontinuous, again, we would have to verify it for every point in the domain. To show that it's not lower hemicontinuous, then, we need only to show that for some point in the domain, the correspondence fails to be lower hemicontinuous at that point. And again, x bar equals 0.5 seems to be the logical, the obvious candidate for a discontinuity here. So let's see if we can verify that this correspondence is not lower hemicontinuous at x bar equals 0.5. Now to do that, we need to find some, just one, some open set V that intersects with the image, because we're now talking about lower hemicontinuity. So we need a V that intersects this, and at the same time, it doesn't intersect with the image of F if we move a little bit to the left or the right. Well, this set clearly isn't going to work. This set V isn't going to work here because it certainly intersects with f of x bar, in fact, contains it, as we've seen, but it's also, as we've seen, if we move to the left or the right, the V will still contain it, and so it'll still intersect it. So that won't establish that lower hemicontinuity fails here. So we need to take an open set V, and let's say, for example, an open set V that maybe goes from 0.6 up to 0.8. So it intersects with the closed interval 0.3, 0.7. And so let's actually do that. Let's suppose that V is the open interval from 0.6 to 0.8. that open set V intersects with the image, the closed interval from point 3 to point 7, but any open interval we take down here, any open set U, any neighborhood of point 5 is going to include points to the right, and for those the image is only the singleton set consisting of point 5, which doesn't intersect with the open interval from point 6 to point 8. So that immediately establishes that the correspondence is not lower hemicontinuous at point 5. And in fact, it is lower hemicontinuous everywhere else in the domain, but just to fail at this one point establishes that it's not lower hemicontinuous on its domain. You can easily show for yourself, I think, that it's lower hemicontinuous at any point over here or at any point over here. Now, you may have noticed that when I went through the arguments about upper and lower hemicontinuity, I, of course, used the definitions. I used open sets V and open sets U down here in the domain, but I also used some terminology that we hadn't heard before. I kind of talked about moving to the left, moving to the right, and what happens to the image when we do that. I think that is very useful intuitively. That terminology is very useful intuitively for kind of understanding, get a better understanding of upper and lower hemicontinuity. And so what I want to do now over here is to develop this intuition, this idea of what happens when we move to the left or to the right. So what I've put on the screen here is a kind of informal or intuitive version of the definition of upper hemicontinuity. So what this says is that a closed-valued correspondence is upper hemicontinuous at a point x bar if no points suddenly appear in the image as we move away from x bar, and then it says in any direction. And actually, there are a couple more words that I find synonyms here, I guess, that are equally good, and that would be instantaneously, no points instantaneously appear, or no points discontinuously appear as we move away from x bar. Now, it says a closed-valued correspondence. Well, so that means this intuition is only going to work for closed-valued correspondences, but I doubt very much that you will ever encounter a correspondence, at least in economics, that is not closed-valued. I can't recall off the top of my head ever encountering in economics a correspondence that was not closed-valued. So what that means is this intuition is pretty universal for working with continuity properties of correspondences. So let's see what this more intuitive version of the definition, if you like, says about this example. So first let's look at upper hemicontinuity. That's what we have here. We've already seen, using the definition directly, that this correspondence is upper hemicontinuous everywhere. So let's see what happens at x bar equals 0.5, because again, that's the place where if there's any discontinuity, it probably would be here. So the image, again, is at x bar is the closed interval from 0.3 to 0.7, and as we move away from x bar to the left, the image remains exactly the same. So no new points are appearing. As we move away from x bar to the right, the image has immediately collapsed down to the singleton set consisting of just 0.5, but no new points appeared because 0.5 was already in the image here when we had the entire closed interval. So no new points suddenly appear in moving away from x bar in either direction. So this correspondence, again, as we already saw, is indeed upper hemicontinuous here. And again, it's easy to see, again, even using this intuitive version of the definition, that It's upper hemicontinuous over on this side because no new points appear as we move right or left. Same thing over here. The image is just the singleton set, but no new points appear as we move to the left or to the right. So this correspondence is indeed upper hemicontinuous on its entire domain. So what about lower hemicontinuity? Well, as you might have guessed, the corresponding terminology for lower hemicontinuity is that a closed-valued correspondence is lower hemicontinuous at x bar if no points suddenly disappear as we move away from x bar. And so how does that work for our example? We've already seen this example. The correspondence is not lower hemicontinuous at x bar. Let's see if that works with this intuition. Again, the image is the entire closed interval, and as we move away from from x bar to the right, what happens? Every point in the image at x bar, every point in the closed interval instantaneously disappears, except, of course, for point 5, because the image has collapsed down to just the singleton set 0.5. So lots of points instantaneously disappear when we move to the right. So this correspondence is not lower hemicontinuous at x bar. Easy to see that it is lower hemicontinuous on this side and in this side. Same kind of argument. So let's do one more example. It's a little different, and see what we get. So here we have a different example, and you might say, wait a minute, this isn't different. It's the same example we just had, but it actually is different. I changed one thing. I changed the image at x bar, at 0.5. Before, the image was the entire closed interval from 0.3 to 0.7. Now the image is just the singleton set consisting only of 0.5 here. So let's see if this correspondence is upper hemicontinuous at x bar. Are there any points that suddenly appear when we move away from x bar? Yes. If we move away to the left, the image at x bar is only 0.5, the singleton set. If we move away to the left, instantaneously, all the points in the closed interval suddenly appear in the image. So immediately that tells me this correspondence is not upper hemicontinuous at x bar, unlike the first example. What about lower hemicontinuity? Okay, as we move away from x bar to the right, no points disappear because now the image at x bar is only the singleton set. We move to the right, it's still a singleton set. So no points disappear when we move to the right, and we move to the left, well, clearly no points are disappearing. In fact, a whole bunch of new points are appearing. So this correspondence is lower hemicontinuous at x bar here. And again, it's easy to see that over here it's lower hemicontinuous, no points are disappearing, and over here it's lower hemicontinuous, no points disappear as we move left or right. So this correspondence is lower hemicontinuous at x bar, in fact on its entire domain. So those two examples, I think, give a pretty good first pass, at least, at the intuition here that we can gain from this kind of informal version of the definitions. I find that this intuition is extremely helpful, at least for me, when I'm working with correspondences and their continuity properties. So I think this is a good place to end the lecture, but I'm going to do an additional video in which I'll go through a number of different kinds of correspondences, different than these, and we'll see which of those correspondences are upper or lower hemicontinuous and which ones aren't. And we'll be using the definitions and these informal versions of the definitions. So I think that'll help a lot in our intuition with correspondences. So that's it for today. See you all next time.